Today we're going to be talking about finding or defining the equations of planes. We have previously talked about planes in this course, particularly the intersection of a line and a plane. The term itself shouldn't be new to you, but visualizing a plane or picturing a plane in 3 space will probably be a new concept for you, and it may be a difficult one, so don't be surprised if that's the case, if you're not grasping it right away. My biggest advice, I guess, when you're picturing planes is for you to picture a piece of paper, a flat surface similar or exactly like a piece of paper. When I'm drawing it, I will typically be drawing it like a parallelogram, okay? And that is just something that you will see in textbooks, in questions, other places. So these planes are infinite, and we are able to define them using 2 non-collinear vectors and a point. So we are going to be doing some examples in here. So our first definition is the vector equation of a plane. The vector equation of a plane is a plane in 3 space determined by a point A, I just called it A1, A2, A3, and 2 non-collinear vectors. So in this case, I just say U and V. The vector equation is x, y, z is equal to A1, A2, A3 plus S times U1, U2, U3 plus T times V1, V2, V3. If you're wondering why this looks familiar, you will notice that it is very similar to our last unit, except now instead of just 1 direction vector, we do have 2. That is the difference between a line and a plane. I guess one more thing that I do want to mention before we move on is the fact that I just kind of skipped over the fact that we have an S and a T in our equation right here. So the S and the T are parameters, just like in the last chapter. So we do probably want to include the fact that they are both elements of the reals. So what that basically means is that you can choose any value for S and any value for T, and we could plug that in to get some points on this plane. Just like previous lessons, we can use the vector equation of the plane that we just defined above, and we can write the parametric equations. So in the exact same way that we did it yesterday, we can write our 3 equations. So the equation for x, the equation for y, and the equation for z. I do need to take a look at each component again separately. So x is equal to a1 plus s u1 plus t v1. Y is equal to a2 plus s u2 plus t v2, and z is equal to a3 plus s u3, oh my goodness, I am so sorry guys, plus t v3. And just like yesterday, I do need to say S and T are elements of the reals. So in previous lessons, we were able to find the scalar equation of a line. In 3 space, it won't really work the same, and we are not able to define the scalar equation of a line in 3 space. What we can do is we can define the scalar equation of a plane using a formula that's very similar to what we have previously talked about. So the scalar equation of a plane can be written as ax plus by plus cz plus d equals 0. So just like when we were writing the scalar equation of a line, we came up with a normal vector. We can do the exact same thing. We can come up with a normal vector to this plane, and it will be the components a, b, c. So what that basically means is that if you picture a plane, again, I want you thinking of a piece of paper, I can create this vector n, my normal vector, that is perpendicular or 90 degrees to that plane. And again, its components are the a, the b, and the c from the scalar equation. So during this example, we will be going through all of the key components of creating an equation of a plane. So for this specific example, we have points A, B, and C, and I'm asking you to find the vector equation of the plane. So you know from the previous slide that if you're looking for the vector equation of a plane, we do need 1 point and 2 direction vectors. The direction vectors that you choose to find are really up to you. If you do it right, your equations will look different, but if you were to plug in points, they would be satisfied in the same way as, say, your friend who used, different vectors. So just because I'm lazy, I am going to be using AB for my first direction vector, and if you remember, I need to be taking each coordinate and subtracting the other. So if I'm finding AB, it will be -1 take away -1, which is 0. 2 take away 3, which is -1, and -1 take away -2, which is +1. So again, maybe you want to use BC for your next direction vector. That is totally up to you. I am just going to use AC. And when I do that, I'm going to get the exact same way. 4 take away -1, so 5. And 1 take away 3, so -2, and -2 take away -2, so 0. Now, for this next step, when I'm actually writing my vector equation, on the previous slide, I used component x, y, z is equal to, and here, just because, again, I'm lazy, I'm just going to be using vector r is equal to. It really doesn't matter. It means the exact same thing. I need to choose a point. Any point will work. I'm just going to choose point A because it's the one that I see first. So 1, 3, -2 plus my parameter s times my first direction vector. So 0, -1, 1. Make that look like a negative there. Plus parameter t times my second direction vector. 5, -2, 0. Now again, hopefully you remember S and T are elements of the reals. Now that we have our vector equation, it is really easy to find our parametric equations. So all I did was copy the parametric equation from the previous slide, just so that you have it on this screen again. Again, I'm really sorry, I still can't find any pen that works really well. I'm sure you can tell how frustrated I sometimes get with what my iPad is doing when I'm writing. So we need to remember that I labeled this vector r, but really we know that this is the exact same as x, y, z. So when I'm writing my parametric equations, I just need to do one component at a time, and I need to work my way through the equation. So x is equal to -1 plus 0s plus 5t. Y is equal to 3 minus 1s minus 2t, and z is equal to -2 plus 1s plus 0t. Now, I can simplify those a little bit. Writing the 0 is not necessarily needed, and so I can simplify those to, maybe I'll just do it down here. X is equal to -1 plus 5t. Y is equal to 3 minus s minus 2t, and z is equal to -2 plus s. Now again, s and t are elements of the reals. In part C, we're going to be finding the scalar equation. So what I've done is I've just brought the two direction vectors that we found in part A, so vector AB and vector AC. These vectors represent the edges of the plane, if that's the way that you want to think about it. We do know that if we're writing a scalar equation, we do need the normal, and when we're doing that, we know from previous knowledge that we can easily find the normal if we have two direction vectors by simply taking the cross product of those direction vectors. So I'm quickly going to show you the cross product. I know that by now you are pros at doing it, so I'm not going to take as long as I normally would. So if I was going to do the cross product of AB cross AC, I'm going to start with that middle component of AB, so -1, 1, 0, -1, followed by the middle component of AC, so 2, 0, 5, -2, and from here I can get my components. So -1 times 0 minus -2 times 1, so 2. 1 times 5 minus 0 times 0, so 5. That's a really silly looking 2. And 0 times -2 minus 5 times -1, so 5. Now, if you remember correctly, we did say that the normal is just A, B, and C. So knowing that, we can fill out quite a bit of the scalar equation that I previously gave you. Ax plus by plus cz plus d is equal to 0. In order to fill out everything that we need, we do need to use a point. That point does not matter, so I could be using the point A, B, or C that I gave you in the original equation. I am just going to be using point A, which, let me look back here, -1, 3, -2. So if I'm plugging in my A, my B, and my C that I found by finding my normal, and I'm plugging in my X, my Y, and my Z from point A, I can isolate and solve for D. So 2 times -1 plus 5 times 3 plus 5 times -2 plus d equals 0. -2 plus 15 minus 10 plus d equals 0. And that leaves me with d is equal to -3. I'm really sorry. I hope that you are writing your own note as you go along. I could not fit my final scalar equation on that page. I should have planned ahead and wrote a little bit smaller, I guess. But if I am writing my final scalar equation, so therefore the scalar equation is 2x plus 5y plus 5z minus 3 is equal to 0. So again, I'm using my A, my B, and my C that I found by doing the cross product, and I'm using the -3 that I found by isolating for D after I plugged in any point. So the next part of this question, part D, is asking if a specific point P, 3, -1, 1, lies on the plane. So if you go back and you take a look at the 3 equations that we found, it doesn't really matter which one you use. We do typically want to use the easiest one, kind of eliminate as many possible mistakes. I'm going to be using the scalar equation. I'm sure you probably agree that will be easiest. And what I need to do is I just need to sub in the point P and kind of do a left side, right side check. So if I'm looking at the left side of my equation, I have 2x plus 5y plus 5z minus 3. And if I'm looking at the right side, I just have 0. If I go ahead and I plug in my x, my y, and my z, I get 2 times 3 plus 5 times -1 plus 5 times 1 minus 3. So 2 times 3 is 6, plus 5 times -1 is -5, plus 5 times 1 is 5 minus 3. 6 minus 5 plus 5 minus 3 is 3. Therefore, what I've just proved is that left side does not equal right side, and point P is not on the line. And I should have said plane there. Sorry about that. Point P is not on the plane.